began last time to discuss the reaction of various vacua to the change of the frame. And it's physically important phenomenon which we encounter in quite a few situations, starting from the most familiar and the oldest one is what I started with, the superfluidity, and it continues to many, it applies this type of consideration to many cases, including quark confinement and including radiation of black holes and radiation of accelerated detector in Minkowski space-time. It all has the same origin in a sense, same kinematic origin. I remind you what we did. We did two simple things last time. First, we looked at some, say, water or superfluid, well, any matter, and we assumed that we have Galilean symmetry, and we actually looked in two ways. One was the question whether an external body moving inside, whether it experienced resistance. Experience resistance, and obviously in superfluid situation it doesn't, in normal fluid it does, but what does it mean, experience resistance? It means that it loses its energy by radiating excitations of the fluid. So the energy of the moving body is transferred to the energy of the fluid. And it was a simple Landau criterion. If E of P is the energy of the moving body, then we said that if we emit, say, one excitation omega of k, conservation of energy tells you that we have this. I'm just reminding you. And therefore, we have the condition that Vk should be equal to omega of k. And if this cannot be satisfied, then there will be no resistance to the moving body. That's the case of superfluid when omega is Ck. Now, for the same reason, we mentioned it briefly, so I'm just repeating, a particle which moves with a speed higher than speed of light, which is possible in if you are in some medium, then it radiates Cherenkov radiation. I also looked at somewhat more complicated case, but that we will not. When you have this, when we have waves on deep water, and the ship, when it moves, it produces two. It's called Kelvin's wake, but it's a bit complicated. It actually has to do with caustics and so on. I thought later that I should have given you not this example, but a much simpler example when you have shallow water. In the shallow water, you have, if you have the wave, which is, all these waves are extremely easy to find. You will find them at the beginning of Landau Ilish's book, the derivation for the spectrum. It's very simple. And it actually is Ck on shallow water when the wavelength is much larger than the depth. And c is not a speed of sound, of course, but something very easy. What do you think, by the way? Suppose we have, I'm digressing as usual, we have depth h and we have g as acceleration for the free fall. What would be your guess about the, if I tell you that this is the spectrum, that's easy to find, then what would be the order of magnitude of this effective speed of sound? Yeah, it will be basically the speed which the body acquires falling from this altitude h. So it's very everyday kind of object, and you of course can observe the Mach cone. The Mach cone is the solution of this thing in this case. With when h goes to infinity, actually the solution in the Landau-Lifshitz for omega you will find for, it's immediately found for all values of k. And in linear part is very easy. Non-linear, of course, is much more complicated. For the deep water, it's a bit different because omega is not k; it's square root, contains square root, and so on. If actually, well, I will not go into this. Anyway, that's one way of thinking. I'm just trying to convey some methods of thinking about such problems. And I'm doing this by considering various examples. Another way of thinking still about the same problem is to say that we make, it's more general, although it is as simple as it could be, this type of logic. It's slightly less simple, but more general, is to analyze Galilean symmetry. And in the case of the Galilean symmetry, we say, I'm still repeating, but I will soon start saying new things. We say that energy is transformed like that. That's the law for energy transformation in non-relativistic mechanics. And and here we see very clearly a possibility for the frame dependence of the vacuum state. What do I mean? The vacuum state at rest is some ground state for this fluid. The first excited state for this fluid is E0 plus some elementary excitation, epsilon of p, which in superfluid will be simply the sound wave. And so on. There are many other levels. And obviously in the rest frame, this is larger than this. And we have this vacuum. Now, as we go to the moving frame, the difference between E1 and E0 is epsilon of p plus pv minus pv, excuse me. And you see that this excitation, this first excited state from the point of view of moving observer is a ground state, actually. Or maybe not even the ground state, but it lies below the original vacuum. So it's not the vacuum anymore. And actually that's the reason basically for radiation of accelerated observers, the black holes and so on, and we will see this. But now we need one more type of logic to analyze this phenomenon. Yes?
Do we neglect the mv squared?
But it cancels because you see, it's the same here and here. We certainly don't neglect it. Okay. Moreover, it will, in a second, it will appear on the blackboard in a different shape. So let's now go a little deeper. Let's look at the Bose gas, the Hamiltonian for the Bose gas in second quantization. We have second quantization operators, and we have something like 1 over 2m d alpha psi square minus mu psi dagger psi, that's the chemical potential, plus some interaction. It doesn't really concern me what it is precisely. Roughly speaking, it's something like that. And the if we want, and that describes the superfluid at rest. Now we want to make the Galilean transformation and see what the Hamiltonian will be. What would be your suggestion? What's the change of psi of x will be equivalent to the Galilean transformation? Yes. Actually, if you substitute psi what will happen is that you have d alpha psi will change to d alpha plus imv. Very soon I will set m to 1. It's not really d alpha. And when you take a square, all these terms are, of course, invariant. The only change, h will go into original h minus vp plus mv squared divided by 2, where m is just m integral psi dagger psi d3x. We integrate it over d3x. So that's the total number of particles. P, the total momentum, is m psi dagger d psi. So it indeed, this phase change is this normal, is just this gauge transformation corresponds to Galilean transformation because the Hamiltonian behaves as it should, and the momentum also behaves as it should. Yes?
Direction, delta function direction?
Yes, it's a delta function direction, but if it is not a delta function, it doesn't change anything. Let's write it down for the general interaction. So these terms cancel. Okay, now let's try to understand how the system reacts to the Galilean transformation. And there are and at this point, what will appear is the polarization operators for this system. Namely, we will study first a little bit more general question. Namely, what will happen if you add some external electromagnetic field to the system, which simply means that I want first to replace d alpha by d alpha plus I a alpha of x. And then we will see what happens then. We go, in a sense, this Galilean transformation corresponds to the constant shift of the vector potential, and we will see how the system reacts. And it turns out to be highly non-trivial. Okay, so we have to analyze. Let's discuss some general things first. When we have a many-body system, it's characterized by density and by current and by some other variables. We actually have the polarization operators. We say, let's, for example, let's impose external field A, and let's discuss how which current it induces current in the system. And well, I will will be using at the moment momentum representation. So we have P alpha beta. It's more or less similar to what we did when discussed two-dimensional quantum gravity. K omega, delta A beta. And we also have components. This probably this is if this is spatial components, then there are also components pi 0 0. Let it be, say, okay, let alpha be 0 1 2 3, and then I will use Latin alphabet to describe 1 2 3. So we have, generally speaking, pi 0 I and pi ij, all functions of k and omega, in order to describe the system. However, some of these functions are not independent. How can we reduce the number of independent reactions? This function describes various reactions to various fields. How to reduce this number? Current conservation, which effectively can express these terms containing 0 time component through this one. And the polarization operator, in general, we can write it down as pi transverse of k omega. It's just a convenient decomposition. Now, the very important note, and then pi 0 0, of course, and pi 0 I, using current conservation, can be expressed in terms of the longitudinal polarization operator. It's, so to say, spin 0 part. And there is also transverse thing. The most important thing which reflects various behavior under Galilean transformation is what happens in the limit when k and omega go to 0 in various order. As we will see momentarily, things will depend on which order. This limit is highly non-commutative, as we will see. Now one more comment. Why it was to be expected to have two independent functions here. It's how it is related to some macroscopic electrodynamics, which you know. Yeah, well, there are only two. There are epsilon and mu, and there will be one of the exercises which I suggest is that you simply establish, maybe part of it we will do on the blackboard because I will need this relation, establish the precise connection between dielectric constant or permittivity and permeability and these polarization operators. It's a trivial exercise. It's a very easy exercise. Slightly more difficult exercise will be to do the same counting and the same thing in the gravitational field. So you have to figure out how many gravitational analogs of epsilon and mu exist. Anyway, let's now derive some general sum rules. We will need them to discuss this problem. First of all, we assume that we have a perfect translation invariance. And I want to know, I claim that it is possible to have some very general expression, to derive some very general expression for pi ij at omega and 0. Try to think what kind of reaction. Imagine you have a box with electrons, an infinite box, so you have translation symmetry. And you apply electric field, which is, well, time dependent in general, but homogeneous. That's k equals 0 corresponds to the homogeneous fields. So what will happen to this electron gas when you apply some weak field? Something very simple will happen, almost trivial. But
Oscillate or something.
no, they will. If the field is constant, they will start accelerating as a whole, which means let's write down the equation, the Newton equation. I shall keep for one moment those E and M, but I will later be setting them to 1. A great economy of chalk. So you have this, and if we go to momentum representation, this is clearly this. A depends on T only because we don't have space dependence. So the current, we obtain the current by multiplying it by density, and we get an E divided by M A, which means that pi ij, now I'm setting these guys to 1, omega and 0 is equal to density. Which means that and that's this is some, by the way, if you want a deeper understanding of this, or not doing this, you of course can remember that all these pi ij and more generally pi alpha beta is, if we're talking about free system without interaction, it's simply the diagram, the photon mass, photon polarization operator. So what I would suggest is this is particle, there is the photon, which creates a particle in the hole in the free case, and in any textbook you can find the expression for this thing. And it's interesting to see how these naive sum rules are really realized in this diagram. By the way, here it's not precisely the case which will interest us. We will be interested in bosons and in in interacting system. But this is the simplest, the fermions. I think the best source which I would recommend to read about these things, not about these things, you will not find this. I don't know where to find it, but to analyze polarization operators and things like that, the book by Abrikosov et al. Is the best, definitely. It's an excellent book called, I don't remember how it was, the title, but you know probably. So that's one thing. By the way, since we talk about this, it's clear that as I told you about an exercise, to find precise relation between the two, let's notice that if omega is equal to 0, so we're talking about static fields, let's find let us find how the system reacts to magnetic field. The reaction to magnetic field will be described by this term, because we can always write down the magnetic field B as and you probably can figure out what's the relation between magnetic permeability. Remember, the magnetic permeability enters as 1 over mu B squared term to the effective action. And here we have this thing. So what's the relation if you have finite magnetic permeability? Well, it's just 1 over mu will be k square over mu. To cancel this k square will be equal to pi t of k and 0. And we can always choose the transverse gauge in which the vector potential is divergence is 0, so that the longitudinal part, roughly speaking, the rule of thumb is that longitudinal part contributes to dielectric constant, while transverse part to magnetic thing. It's not precisely correct, but roughly speaking, that's the situation. One more generality, I think it's actually, to understand these things, it's quite important to play around with them, and you should yourself try to look at various physical situations and see how they are described by those quantities. I'm not yet finished and not yet ready to pass to this thing because we need a few more facts about polarization operator. As we will see a little later today, the superfluidity corresponds to mu equal to 0. We will see what it really means. But before that, one more thing. So, and all that you can see, you can look at the book by Abrikosov-Garikov-Salashinsky, which is, as I said, is the best, and see the expressions, concrete expressions for polarization operators when they discuss Fermi liquid. And they are not checking there that all these sum rules, but you can do it, and it's a very useful exercise. One more thing, which you will not find in this book because it came much later. Let's suppose, so here we have three green functions for Fermi gas. Imagine that these fermions, these electrons, are in magnetic field. So without magnetic field, we have this decomposition, which is dictated. We have only two functions. Now imagine that we are in 2+1 dimensions, and we put fermions in magnetic field. So these green functions will be the green functions in the magnetic field. What will be there will be one more possible structure because of that. Yeah, we can have, it should be proportional to magnetic field, epsilon alpha beta gamma. And as you see, it's clearly Q gamma. It clearly satisfies current conservation. Q alpha pi alpha beta is 0. Why we didn't consider it before without magnetic field, and why I put the magnetic field here?
Because it's still the scalar, and epsilon is dependent, so this is a two density.
Yeah, it was time reversal invariance, which is broken by magnetic field, which is now allowed. This is now the allowed term. And as you see, it gives you variation of the induced current will be, say, in direction x, will be epsilon x y 0, qy a 0, and this is just the expression sigma xy ey. E is the electric field, so this is just the Hall effect, which is described by this diagram. It takes a little more to argue that it's it is quantum Hall effect and some without interactions, integer Hall effect with interactions. We will see something very similar. There is certain analogy between the quantum Hall effect and particle production in electric field. We will discuss this later in the course. Anyway, so this was just a side remark for your orientation. Notice, by the way, that all this is relativistic formula, but if you remember that it's non-relativistic problem, it will not change anything. There's no other structure. There's only one structure which fits all the conditions. Okay. Now, we are not finished yet. We found that transverse thing. We see that something strange is happening. Namely, we derived the relation that this is equal to the density. At the same time, now we can put omega to 0, k to 0 here, and we get a contradiction. We get the conclusion that magnetic permeability must be zero, some nonsense clearly. So what do you think? How this relation is just the definition of magnetic permeability. This is the sum rule, which is correct, and we want to set k and omega to zero in both formulae, and they become incompatible. It contradicts to the fact that there are. Yes, actually that's the point. But what does that mean? That means that pi of k and omega have singularity at omega and k equal to zero. And singularities in quantum field theory, they mean that there are some excitations which starts being created at this point. So let me explain this. We will explain this in a moment, and this, I shall give you another case for the. Let me first tell you what will be the outcome, and then I will find. The outcome will be that when you have free electrons, then you have singularity at k and omega equal to zero coming in both functions pi t and pi l. What would be so that is if we discuss Fermi gas with non-interacting Fermi gas. And as I said, singularities must be the consequence of some gapless excitations in the system. Which excitation could be responsible for this singularity at omega k equal to zero in the ideal Fermi gas? Ideal Fermi gas. No, it's neutral. There are no plasmons. It's just it's the simplest. The excitation are extremely simple in. Well, not quite. Remember, we have a box, and we have energy levels which are occupied. There is Fermi energy, let's call it, or chemical potential mu, and all these levels for energies less than mu are occupied. That's the ground state of the Fermi gas. Now, what are the simplest excited states? Yes, we can take we can have change of energy, which is epsilon of P2. Epsilon of P is, for ideal gas, is simply P squared divided by 2m, minus epsilon of P1, provided that P2 is greater than Fermi momentum. This is Fermi momentum here, and its square is chemical potential. And P1 is less than Pf. So you have particle Hall excitation, and their energy can be made as small as we like, because you can always take the particle closest to the Fermi surface and move it infinitesimally. So you have this massless excitation, and what does that mean? Try to think about it, that it will contribute both to pi t and pi l. Both things will have singularity at k omega 0. what it means physically, that what kind of excitations you expect to thinking of their spin, or better to say angular momentum, well, you can say spin, the contribution to pi L and pi T. Transfer, what?
Transversal longitudinal.
Transfer, yeah, but actually it's angular momentum 0, which contributes to longitudinal, and it's angular momentum 1 to contribute to the transverse. And these guys, particle and whole, can have any angular momentum, so they do contribute to both cases. Now things become completely different, and so you have this thing. You have mu, which is a constant, which you obtain by calculating this diagram, of course. And actually, an exercise will show you that mu is less than 1, coming from this diagram. And it actually has a special name, this phenomenon, that electrons they produce some reaction to magnetic field. It's what is called Landau diamagnetism. It's a diamagnetic contribution which tends to screen the applied magnetic field. By the way, I'm maybe overwhelming you with various analogies, but there is another wonderful analogy, because if you look at the relativistic calculation for fermions in the vacuum, this Landau diamagnetism is precise analog of the behavior of effective charge, of screening of electric charge in quantum electrodynamics. In quantum electrodynamics, and it all sits in this simple diagram. If you introduce into the vacuum a charge, you create electron-positron pairs. And they are more likely to screen this charge than to anti-screen. And that you can trace this calculation precisely to the diamagnetism in this case. And by the way, what is the? When I say it actually screens, it might be unclear a little bit. My argument is that a mini puzzle could be that, okay, it's neutral. It's a dipole which is created. So how it is possible for the dipole to screen the charge? Any comments about that? On the other hand, we calculate the diagram and find screening of the charge.
Of course, they're neutral, but like you choose the surface.
Yeah. Yes.
Between plus and minus in dipole, we'll see that you have some.
Yeah. Well, more. Yeah. Actually, you can say that we measure the charge using Gauss theorem. So we take a large surface surrounding this, and there are those dipoles flying like that, and they will not change the total flux through the surface. However, there are also dipoles.
Yeah, but we will have like dipole that lies on the boundary, and they will change.
Yeah, that's what I'm drawing here exactly. They will change it, so it's a little bit. You can actually do the calculation using there is a 18th century problem in probability theory. You throw the needle and you want to calculate the probability that the needle crosses the boundary. What?
It's equal to pi.
Sickle?
It's equal to pi.
Something like that, but here it's more, you have a distribution of length for these dipoles, and so it's a little bit tricky to, it's not simple number. Well, it is simple number, which is one loop beta function. It's just the one loop beta function, which originated in 18th century. Okay. So returning to our stuff, this was free case, and now I shall mention the superfluid, and then we will return to the problem which I started with. In the superfluid, the general situation is different. First of all, basically what I will tell you what really happens in superfluid. There's no singularity in pi t. There is the transverse part is analytic at k and omega 0, so that actually, the consequence of it are very drastic. Let's first understand why we should expect that the transverse part has no singularity. What do you know about the elementary excitations in the superfluid? Or, for that matter, let's talk about fermionic system first. It's slightly easier. So superconductor. Excuse me for mixing it. So what do you know about spectrum in superconductor? It has gap. Therefore, the diagram like that will not actually give anything. Will not have a singularity at k equal omega equals 0. Therefore, we find that pi t at omega and 0 as omega goes to 0. This is sometimes called, there's a convenient name. This was called the omega limit. It's equal to n. That was our sum rule. But the k limit, which is this thing, again, it's called sometimes, maybe not very common, but nevertheless used. It will also be n. So this time, the diamagnetic, magnetic permeability will be 0. And let's write down the expression for the which current is what? It is pi t, we send k to 0. Pi t must remain constant as we send k to 0. So mu should behave as k squared as k goes to 0. So mu, it will be clear in a moment. So we have this general thing, and let's choose the gauge in which kj, which in space the divergence of A is equal to 0. Then you get the very famous and important equation, which is called the London equation. I remember I set electric charge and mass to 1 by choice of units, and the current is given by this. And now let's see what it means. It means that in the superfluid, the equation for A, we have I remind you, we have in Maxwell equation we have curl of B. It will be the Laplacian of A perpendicular, and we get the equation. And I'm considering time-independent case, static case, so that's all. In the dynamic case, there will be also terms with time derivatives. But what's very important is that now we have the effective mass. The vector field acquired a mass. So as a result, the magnetic field cannot penetrate it, exponentially damps if as you go inside superconductor. And that has two names, actually. In condensed matter physics, it is called the Meissner effect, and this is the London equation. Precisely the same thing in particle physics is called the Higgs mechanism. That's all is the purely kinematic consequences of this. And we now will see, we now are practically ready for the analysis of Galilean transformation, and we will see when we have to expect superconductivity and when not. So you see how much, I actually didn't exhaust the subject, we have to move. How much you can learn by studying some simple polarization operator and by putting back and by considering back reaction. It's the back reaction. You impose a perpendicular or magnetic field, you put it back and you get this thing. And instead of the magnetic energy, as I mentioned here, you see how many various analogies. Diamagnetism corresponds to screening of the charge. By the way, this in the Young-Mills theory, you have basically the same picture and you have the same Landau diamagnetism. You have screening, but you also have what is called Pauli paramagnetism. Pauli noticed that apart from Landau effect, which is diamagnetic, since electrons have spin, they tend to align along magnetic field, and that makes a paramagnetic contribution. In normal matter, typically, they can be various sizes, these two contributions. But what's important is that in the vacuum, in the Young-Mills theory, Pauli paramagnetism overtakes the Landau diamagnetism, so you get asymptotic freedom, anti-screening of charge instead of screening. Quite interesting. So you see, I'm going fast here, and I have to go fast because there are so many important things remain. But it's all worth homework. You just sit and try this and that. It's a lot of fun. Try to understand various phenomena. Try to understand the integral Hall effect use where it was. So many things to think about. And the last comment about this Meissner effect is that in the magnetic energy, it's in the paramagnets in the normal matter, it's 1 over mu b square. In the case of the superconductors, what do you think will replace this this formula? Look at this and
Pi ig.
what?
It's always pi ig, ig, but we have to re-express it.
Yes. But right, yeah, that's the way to approach it. And if you do, you will get inverse Laplacian, the green function B. So the magnetic energy becomes non-local in that case. Okay, now back to the original problem. I erased it unfortunately, but I shall write it down again. So we have the Hamiltonian. This time I will be setting masses to 1. And again, to simplify writing, I put the delta function direction, but it doesn't change anything. What's convenient, the convenient change of variables is the following. Let's take psi to be equal to consider modulus and the phase of this guy. Then you will immediately get the following, that the Hamiltonian will be gradient, it's proportional to gradient of rho square minus mu rho square plus g rho to the 4th. Plus all this doesn't, the concrete formula here is not important. What is important will be the term rho square gradient of phi square. Now I will say the following. For the analysis of this type, the raw degree of freedom is completely irrelevant. The relevant thing is this last term. Why do you think? What are the grounds to say that? What's the difference between the raw excitations and phi excitations?
Rho has average.
Rho has average, but moreover, if you look at the oscillations near the average, they have a gap. They are massive. And we are looking at things at very large, we are interested in things in the deep infrared. And then we get something very simple, namely something that the Hamiltonian is rho is some constant, so I put just some proportionality here. it's just a free field. It seems to be a free field. Actually, we will consider various dimensions. So,
isn't a superconductor just a charged superfluid?
what? Oh yes. Well, the difference. You see, it is a charged superfluid, and what is very important? There is certain subtle difference between superconductors and superfluids, which is you have to account the Coulomb interaction. There is a long-range interaction in superconductors, which changes things a little bit. But at the moment, we are not considering this. We are considering. I'm saying that we are imposing external fields, but we do not assume at this point. We do not assume that there is interaction via this field. It's an external field only, which we use. Namely, I'm going just now. I'm going to use to impose external I consider it as a charged superfluid, but the Coulomb interaction charge is intrinsic charge is so small that Coulomb interaction is negligible, but you have external field, which is important. What I'm saying is this. That's in the. I already told you that here we have to change d alpha plus I alpha to see the reaction towards the reaction on the electromagnetic field. And now it will be simply d alpha phi plus A alpha square. So it seems to be very, very trivial and simple. It seems to be the way to calculate immediately the polarization operator. And it is, but it leads us to a wrong conclusion, actually. We see that we can always write, we have it is quantum fluctuations are not important, so we just take the partition function of this kind. With quantum we will get the same results. I will explain why. It's very simple. So let's consider this functional integral. And it's e to the minus beta f of A. F is free energy. And it seems that we can always calculate the naive calculation. Calculation of F. The answer will be simply that F is proportional to A alpha perpendicular square. Which means that how I obtain this result in the first place. You simply decompose A alpha using these projection operators. These are projection operators. This is transverse projection. This is longitudinal projection operator. You can always split A alpha to A alpha perpendicular, A alpha parallel, and you can always also choose the gauge in which A alpha parallel is 0. And in this case, we simply have d alpha phi plus A alpha square is equal to A alpha perpendicular square plus d alpha phi square. They do not interfere between with each other because you can integrate by parts and get the divergence of A here. So in the transverse gauge, by the way, remember the London equation was that it's NA alpha with perpendicular A alpha. It will be certainly the wrong formula if in the general gauge. You can find this, write down this formula in the arbitrary gauge, the London equation. Now that's precisely what we get is the London equation. If you vary free energy with respect to A, that's the current. The current, by definition, is the variation of free energy with respect to vector potential. Then you get the London equation. But there's one embarrassing thing about this derivation. That's why I call naive. The embarrassing thing is that it works for all It's not that it is too simple. It's very simple, but that's the advantage. However, it tells you that for all possible temperatures, the system will, for all possible betas, the system will be a superfluid. This Bose gas will be a superfluid. At the same time, it's quite that's quite obviously is wrong. So we get too much of a good thing, not superfluidity, but proved a little bit too much about it. And the resolution of this paradox is extremely important and interesting. The resolution, roughly speaking, is, I'll put it in words first, it's that when we integrate over phi here, phi is not a simple Gaussian field. It's a field defined modulo 2 pi. And we must account certain defects called vortices, which will be responsible for destruction of superfluidity at high enough temperature. And again, there are a huge number of analogies. For instance, we will see that there's completely analogous treatment of quark confinement. There's analogous treatment of so-called dislocations in solid state, in crystals, and so on. So let me explain a little bit and what I'm talking about. Okay, we have still some time. Still have some time. Okay. Remember that when we represented psi, we said that psi must be, of course, non-singular and univalued, but phi doesn't have to be univalued. It could be that we have a singular point, and as you go around singular point, phi changes by 2 pi n. To make it more plausible to you, the effects which I shall first probably will give you a completely trivial example. Consider a particle, a free particle on a line, moving on a line. Its action is integral x dot square. And quantum mechanics tells us that we have to calculate the amplitude, you have to calculate functional integral over these trajectories. Now, and you will get some amplitude for transitions from one point to another. Now let's consider, instead of the line, consider a circle. So here we have, consider a circle. The action on a circle is the same. X is now coordinate on the circle. But we know it should be two different answers for the simple. What would be the simplest reason to expect two different answers in this problem?
It's a different set of functions.
Yeah, but even more strikingly, here we have continuous spectrum. Here we have discrete spectrum. So it's totally different things. So how we here the amplitudes are given by the Dirac-Feynman formula, e to the is. Here also it's given by this formula. But what's the difference between this and this?
Winding trajectories.
Actually, yeah, well, in a sense, yes. What it is allowed, if we discretize it, we can, or not discretize it, we can have a discontinuity. We allow not only continuous trajectories, but trajectories with discontinuities equal to 2 pi n. So, which means that it's something very concrete. Namely, when we talk about a particle on the line, we have the action. We discretize it to calculate sum over t, xt plus 1 minus xt square plus, that's it actually. And that is the, as epsilon goes to 0, you see that the trajectories must be continuous. What would be the correct discretization for the circle case? What we should allow, we should remember that xt is an angular variable.
Must add 2 pi n to the
That's right.
n sum of
That's right. We should have, we can write down, for instance, like that. We have this term, we add 2 pi nt here, and we prescribe, when we perform functional integral, we say that you must sum over all possible nt apart from integrating over x. And in this way, that's you can check yourself. In this way, you will it's all very simple. You can reproduce the discrete spec you obtain by introducing those defects, so to say, the nt discontinuities. You actually get the right result. It's fun to play it around, although I think by now you find it in many textbooks, maybe. I don't have a ready reference for you, but I would guess it's... Now, in fact, the vortex which we have to add to the system is the following. You can also write down, define it on a lattice in an interesting way. From what we discussed before in this course, what's the closest thing you remember? There was one thing which was pretty close to the definition of the vortex, but not the vortex. Yeah. Definition of disorder parameter with tails on a dual lattice is precisely is very much similar to definition of the vortex. I shall very briefly, don't want to spend time on the lattice. We have a lot of things to discuss. But definition of the vortex, you say that first of all, you define variables phi t on a lattice, which are changing from 2 pi to 0. And you take a dual lattice, just as we did with the disorder parameter, and you choose a tail. It's precisely which goes to infinity. And and now the difference. You define the action which each link gives you phi x minus phi x prime square if the tail is not crossing it, and gives you phi x minus phi x prime plus 2 pi n square. So it's just like in the Ising model, you are modifying the coupling by adding these 2 pi n, and that's analogous to this thing. I suggest that you play around with this yourself. We will not really need this lattice definition of the vortex. What we will need is the continuous definition of the vortex. And the vortex is a classical solution of the equation Laplacian phi 0, but this solution is not the usual one. It doesn't have to be univalued. Namely, phi, we can choose phi as being qa, logarithm, imaginary part of the logarithm, z minus za. That we will probably discuss next time. And you see that when you rotate around the point z, logarithm acquires a pi, so we probably should add 2 here, and qa must be phi is multivalued. But notice what's interesting, that the gradient of phi is univalued. It's a good function, although it has a singularity at the origin, at the position of the vortex. But that's we will see how to deal with it. So the vortex has the feature. No, there are no delta functions. Delta functions would be for the real part. That's the key. It's not the green function, which logarithm of absolute value of z. It's very good that you raise this, because it's important difference to be understood. The green functions, it's singular at coinciding point, but it's univalued. It's not multivalued. Phi is multivalued. Phi has the feature that if you integrate around some contour, it's equal to 2 pi n, 2 pi q, if the contour surrounds this thing. And as I will tell you probably next time, what we have here, I will tell you that actually, I can tell you it now, that historically similar multivaluedness appeared in the elasticity theory. And what we are discussing is just the defect. I will explain it next time. It's just the defect in the crystals, which acquire their own life. Okay, let's stop here. Getting late.